What's up, you guys? Welcome to part 3, where we will begin doing integration by parts. So, again, just like the previous videos, it's just going to be kind of like a walkthrough integral marathon. So, let's get started doing integration by parts. Okay, first integral x e to the power of 2x dx. Alright, so we're not going to be using the voodoo method or some, what was it, UV, or whatever this is. Like, I honestly do not like that because it's so confusing. You know, if I were to teach something like that, I like to go by like integral f prime g, and then it's like oh, I'm sorry. It's the other way. It's like that, and then it's fg minus f prime g. But we're not going to use any of that. No, I'm going to teach you the ladder method, just this once, and then because I know some classes they don't teach you the ladder method. I don't know why, or the DI method. But I mean, if you're going to get into speed integration, stick with this method. Okay, get rid of the UV, whatever, the long thing. It's not. Trust me, it's not gonna do you any good. So, for those who don't know the DI method, this is for you. So what we do is we take the derivative of here, and we take the integral here. Okay. In this case, I like to derive a polynomial, which is x. And what's going to happen is we're going to alternate signs. We'll be alternating signs. And the way our answer goes is our answer goes diagonally. Okay, our answer goes diagonally. So just kind of be careful. So don't forget that. Okay, so x, and then we're going to integrate e to the 2x. Okay, and then I don't know why I put a parentheses there. Derive x, that's 1, derive 1, that's 0, and then we stop here. Okay, integrate this, it's half e to the 2x. Integrate it again, 1/4 e to the 2x, and then your answer is the diagonal. So it's this times that, this times this. Okay, so what this would look like is it would be, so our answer would be x times this, half e to the 2x, and then this times this. So because remember we have a negative sign here, okay, because of that integration by parts formula. So it's negative 1/4 e to the 2x. So let's see. That is our answer. Okay, and that's how it works. And we're going to be doing that throughout the entire integration by parts technique. We're not going to use the voodoo thing, ultraviolet, whatever this crappy technique that is. We're not going to be doing that. Okay, it's too slow. We're going to start going using with DI method. Now, for those who already have learned this, right? I have a trick for you. So, if you already know the DI method, you know the first thing, deriving this, easy peasy, right? So let me restart this. So what it would look like fast, is you write out your DI. In fact, you don't even need your DI, because let's say like you're very experienced, right? You can start just like, x -1, 0, because you know you're alternating signs. And then here you'll do e to the 2x. And what you do is you draw a line, draw an arrow like that, because you know it's going to be repeatingly e to the x. You do this when you're dealing with like e to something x, right? So we just draw a line here. All you do is focus on the constant. It's a half, square, another divide 2, it's 1/4. Okay. and then diagonal line. All right, so it's e to the 2x, x over 2 minus 1/4. That's what it looked like fast. Let me double check if this is correct. Yes, it is. So, okay, yeah. So that's what it would look like. So again, to get used to that, you just have to do this a couple of times, and you'll get the habit of integrating parts like this, and it'll be super fast. All right. So we have a logarithm. So we're going to be deriving a logarithm. Okay, and then we integrate this. Of course, the reason is because when we derive this, it's just 1 over x. Don't forget to alternate signs. And then the integral of this is just 3 halves, 2/3. Okay, so we have 2/3. I'm just going to put this here, 3 halves, ln x, then minus, see, wait, it's just x dividing this. So it would be 2/3 half, right? I mean, we already integrated this, so it's just this squared. So what you can do is you have your eraser on your left hand. You have your eraser on your left hand, and what you do is you can actually, well, erase this. Oh, well, actually, you do need to erase everything, now I think about it, right? So it's just technically this, except that your constant is squared. So it would be 4/9, 3 halves plus c. I'm just kind of double checking, make sure I didn't miss anything. If I do miss anything or I made a mistake, please put it in the comments. Okay, trigonometry. All right, so this one you got to be careful. All right, so starting off, deriving, right, alternating signs. All right, and then we have cosine. We have cosine of 2x. Integrate this, we have a half sine 2x. Integrate this again. We have a divide 2. This is a negative because we're integrating sine of x. Okay. And then we go diagonal, and then you go ahead, put this x2, so 2x plus 1/4 cosine 2x plus c, and we're good to go. I don't know, I feel like integration by parts is the scariest for me, because I feel like I'm always missing something. I don't know why, but I feel like I'm always missing something. So again, we do that trick again, so we just focus on the polynomial thing. All right, derive this, keep on deriving. So it's minus 2x plus 2, all right, and then 2, and then 0. Okay, we have e to the x, and then it's going to be the same thing throughout. All right, so my answer is e to the x, x squared plus 2x minus 2x minus 2 plus 2. This cancels out, this cancels out. Oh, wow, it's just x squared e to the x plus c. Cool. And then you're done. Cool. Yeah, so it's so much faster doing it that way rather than repetitively e to the x, e to the x, e to the x, whatever. So this is a much faster way. Now, let me give you this one. Okay. E to the x. Well, actually, no. I'll do x to the power of 5 is 5x4. Right. So, let's say, like, this would be tedious. You would go a long way. You keep deriving. The shortcut here is that this is a product rule, right? The one that I showed you, the one that I just showed you, the reason why it was only x squared e to the x, because this is product rule. This was product rule. It's hard to see it like this because the e to the x is factored. So if I wrote it out as x5 e to the x plus 5x4 e to the x, you'll notice, oh, okay, I see what's going on here. Or let me actually, I think it's best if I write it like this. 5x4 e to the x plus x5 e to the x. Then this is f prime of g plus f g prime, right? So this is the same thing as, oh, this is the product rule. So I'm showing you the reverse derivative trick here. This is reverse product rule. So you notice, oh, f is x5, oh, and g is equal to e to the x. All right, I got my answer. And then this answer is to x5 e to the x plus c, and you're done. All right. So this is good to keep in mind. This does appear a lot in advanced or competitive integration bees. So product rule, reverse product rule, is a very good thing to keep in mind. Okay, so inverse functions. When we deal with inverse functions like this, we always derive it. Right, we derive it, and then now you're probably thinking, well, there's no other function. So how do we integrate by parts with this? Well, you integrate one. Integrate one. And now this is, oh, okay, well, this is a bit tricky. The derivative of inverse cosine is negative 1 over square root of 1 minus x squared. So be very careful with that. So this is actually negative square root of 1 minus x squared. Okay, and then of course we alternate signs, and then integrate 1, that's just x. Okay, so what we have here is we have x inverse cosine of x. And then what we do with this, is it's the integral, okay, of this times this square. It's positive because these negatives cancels out. So we have this. Oh, this is just U-Substitution. Okay, so let u equal 1 minus x squared. This du is equal to 2x. Right, this gives us a half square root of u du, and then this equals to negative root u. So this whole integral here is equal to oh, wait, this should be a minus. One minus x squared plus c. So what do we do with here? Well, this is just algebra. By logarithm law, this is just, take the exponent out, so that's just a half of ln of x. Right? That's one of the integrals that we must memorize by heart. So this is just half of x ln of x minus x plus c. Okay, it was one of the 10 integrals that we must memorize by heart from our last videos. So again, deriving ln of x, this gives us negative 1 of x. Again, the alternating signs. So we have that. x4, integrate this, we get x5 1/5. Right? Again, we kind of memorize the process here where, like, when we combine these two in one integral, so let me write this down first. Right? And then minus the integral of this times this. This x will divide this, so this becomes back to x4. Integrating it, I mean, we already integrated it, so it's just going to be squaring this constant. So will be 1 over 25 x to the power of 5 plus c, and then you're done. So you see how it's so crucial to just sort of like memorize the process. When you memorize the process, you're kind of like, oh, okay, I mean, I already know where this is going to lead to. And then, yeah. You're not solving it mentally. You're not solving it mentally, so be careful. You're just memorizing the process of it. Okay, so it's an inverse function, so of course we're going to derive it. There's nothing with it, so we're just going to integrate by 1. Then, derivative of this is 1 over plus x squared. Integrate this, that's just x. So we have x inverse tangent x minus the integral of this. This is just a U-substitution. Alright, you let u equal 1 plus x squared. Du is 2x. That 2, so we're having a half. So that's negative 1/2. Du over u. This is an ln. Okay, so we know where to go from here. So this is minus 1/2 ln of u, which is x squared plus 1 plus c. Okay. I mean, we know the integral of cosecant square. So of course we're going to be integrating cosecant square. Then x, derive this, integrate this. This is negative cotangent x. Be very careful. And then negative ln sine x. Okay. It's one of the standard integrals to memorize. Then we go like this. We have our answer already, so I'm going to start with a positive. ln of sine of x, then minus x cotangent of x plus c. So I'm going to introduce you a very common integration B trick. I call it forced U-substitution. So what a forced U-substitution is, you don't have a derivative, right? You let u equal something, but in your original problem, you do not have your du. Sometimes you're going to force that integral into a U-substitution, even if it doesn't have a du. It doesn't always work, so don't overly do it sometimes, but it is extremely helpful. So in this case, here's how we do it. Let u equal ln of x, right? Because, I mean, it's in the power of 4. Alright, so we let u equal ln of x, right? So how do we get our du, right? So what we do is you solve for x in terms of u. So in this case, e to the u is equal to x. And now we derive both sides, and we get e to the u du dx. So now our dx is e to the u du, and that's what we're going to substitute. Okay, so now we just forced a u substitution, right? So let u equal ln of x, so u to the power of 4, and then dx is now e to the u du, and that's your integral. Okay, this, we just performed a forced u substitution here. All right, cool. And so now, now it's just integration by parts. Okay, cool. I'm gonna keep this at the side actually. U equals ln of x. This is just a reminder that you u-subbed ln of x. Okay. I'm also going to put this here. Okay. And now we go ahead and do our integration by parts, u to the power of 4. You keep deriving it and alternating signs. Or if you're very advanced like me, you could just straight up, you could just straight up answer this. Okay, e to the u, that's just e to the u, and then u4 cube 4b squared minus 24u plus 24. Okay, e to the u, and then we substitute u back in, you know e to the u is x, and then u is ln of x, so this is 4 minus 4 ln cubed 12 ln squared 24 ln plus 24, and then plus c. Will answers get long like this in integration bees? Sometimes yes. You'd be very surprised, and I've seen longer. I've seen longer. Trust me. Oh god, there are much longer answers in integration bee. So this is nothing. but don't let that scare you. Don't let that scare you. Okay. So we are technically done with this. You've probably already aware of this, but again, just for those who kind of needs a little review. So this is a type of a recursive case here. So what I do is, so what a recursive means is like, you keep integrating by parts. Let's say I'm going to go ahead and derive sine 3x, e2x, right? And then we keep going, and then we end up repeating ourselves, just with different constants, and we keep repeating ourselves over and over and over, and it won't stop. Okay, that's what I mean by a recursive integration by parts. So what we do, how we handle that, is we're gonna let this original integral equal to I. Okay, this I represents this integral, this whole integral. So we're gonna let that equal to I. Okay, and then we go ahead and do our integration by parts. E to the 2x. Okay, so this is cosine. Derive this. Alternate our signs. Derive this again. Oh crap! Ooh, be careful with the constant. Be careful with the coefficients. Be very careful, because we're deriving. This is times 3 now by chain rule, and then -9 by another chain rule. Again, we're deriving, so we're multiplying our constants here. Then here, we're integrating. We know it's going to be the same thing, but our constants we're dividing. So this is a half, and this is 1/4. Okay. Now let me just draw this again, just to help you visualize. So again, we're at the same boat, except we just have different constants. We just have different constants, but don't worry about that, right? We're still stuck in the same sine 3x e to the 2x, right? So what this is, so here's what we have. So I is equal to, and then we go ahead and write this out. Okay, we go ahead and write this out. E to the 2x. Okay, and then we have a half sine 3x half minus 3/4 cosine 3x. Okay, but what about this? What about this line? This last line. What this is it's equal to I. Well, kind of. The only difference is we have these constants now. So when we multiply this, we have minus 9/4 I. We have 9/4 I. And what we do with this I is we add it to the other side. So we combine those same integrals. So what we have now is we have 1 plus 9/4 I equal to that whole thing right here that we have, right? And so this is equal to what? That's like what? 13/4? Yeah, 13/4. Right, and then we have what we have here. And what you do with that 13/4 is you divide it, or you you kind of reciprocate it to the other side. And that's your answer for this regular integral. So let me go ahead, erase all this. So we know it's 13 over 4 from the other side. Okay, so it's 13 over 4. 13 over 4. Okay. And so now, this whole integral, we reciprocate it to the other side, which means that we multiply all this 4 over 13. All right, and that would be our answer. So let me go ahead. I have like an eraser on my left hand. Erase this. 4 over 13 plus c. And that's how I would compete, right? Rather than keep on rewriting it, I have my eraser left hand, and then erase some parts, and then keep this as my answer. And then you'll definitely beat your opponent. So yeah, this is how I would do recursive integration by parts. Be extremely careful with constants. Be extremely careful with constants. That will really like mess you up. So again, don't go too fast. Don't go too fast. All right. So do we do integration by parts? Well, there's something sussy about this integral. Let's see, the derivative of this is cosine of x, and the derivative of e to the x is itself. This looks like a product rule, right? So we sort of expand this. We notice, oh, f prime g, f g prime, oh my goodness, this actually matches. F could be e to the x, g could be sine of x. So the integral of this is product rule. So this is reverse product rule. So the answer is e to the x sine of x plus c. See, we did not have to do a very long integration by parts. We did not have to do that. This is just a reverse product rule. Take advantage of that, and you're good to go. Does this look sus to you? Yes, it does, because it looks like a product rule, right? If I just sort of rewrite it, f prime g, f g prime, yeah, this matches, right? F is equal to x squared, f prime is definitely 2x, g is equal to sine, g prime is definitely cosine x. Yeah, this is a product rule. So this answers x squared sine of x plus c. See, we didn't have to do a long double integration by parts. We could just go straight to here. This is all x squared sine of x plus c. Okay, so reverse product rule is very good to keep in mind, right? If it looks like, huh, wait, this and this, they're like derivative of each other, huh? You know, like, you know something is sus, you know, so it's good to sort of keep aware of that. It's like that symmetry trick. It's one of these sneaky things to have in the back of your mind. So reverse product rule, cool. From 0 to 1, x squared plus 1 or e to the x dx. Okay, don't overdo it. Don't overdo it. I know how satisfying it is to do reverse product rule. It's very fast, and etc. But don't overdo it, because this doesn't look sus at all. I don't see any derivative of x squared 2x, you know, or maybe we could add 2x minus 2x and then do reverse product. No, don't overdo it. Do not overdo it. Okay, let's not overdo it. Sometimes it's just easy to just go straight into, you know, if the reverse product rule doesn't look obvious, then don't even, you know, don't tamper with it. Just go straight into integration by parts. Okay, and then This is e to the negative x. Okay, it is not e to the x. Okay, this is e to the negative x squared plus 1. Okay, so do not trick yourself with that. Okay, just because it's at the bottom does not mean it's e to the x. It is e to the negative x. So be very careful with that. And then 2x to 0, alternate signs. And then this will always be e to the negative x, except that we have negative here, positive, negative. Okay. I guess I'll write the positive here. Okay, so we have our answer here. So we have e to the negative x. We get negative x squared minus 1. Then positive, this is negative 2x. And then negative 2. Okay. So write like this. And then we have to evaluate it from 0 to 1. Okay. So plug in 1, we get 1 over e. Okay. And then plug in 1. Here, this is negative 2. Negative 2 minus 2, that's negative 4. Minus 2, that's negative 6. Okay. And then minus. And then we plug in 0. E to the power of 0, that's just 1. Plug in 0 here. Minus 1. Plug in 0 here. Minus 2. So this is negative 3. Okay, so our answer is 3 minus 6 over e. That would be our answer. I'm always checking if I made a small mistake. I always feel like I did something wrong. I don't know. I keep double checking my work. Okay. I think everything looks good. Let's continue. Oh boy, well this is an inverse function. But wait, hold on now. It's squared. So this looks like a little this might be a little nasty to integrate by parts with, right? It's a little bit disgusting to integrate by parts. So let's maybe do a U-substitution with that. Okay. So U is equal to inverse sine. But then where's my du? Right? I don't have a du. But that's okay, because what we're gonna do is we're gonna do a force U-substitution. So let's solve for x. This becomes sine of u equal to x. Derive both sides. We get cosine of u du equal to dx. Okay. So we get u squared, and then cosine of u du. Okay. That is how you do forced U-substitution. And then we have to plug this in, the balance. Plug in 0, that gives us 0. Plug in 1, inverse sine of 1, that's pi over 2. Okay. And now we do integration by parts. Alright, so u squared, 2, 0. Okay. Now, thankfully, because this does not have any coefficients or any constants inside that, what I like to do is I like to abbreviate my trig functions. So I go cosine, sine, negative cosine, then negative sine. Okay. If it had constants, then I do not recommend doing this. I don't recommend doing this when you have constants. Okay. So, because you can easily lose track of your coefficients, and that will ruin your entire day. So if it doesn't have constants, then I like to abbreviate it. Okay. All right. And now we're good to go. We go ahead and solve this. Now, I actually love the balance. I really love the balance, and here's why. Let me first write it out. U squared sine u. This is, let's see, negative, negative, that's positive, so plus 2u cosine of u, and then minus 2 sine of u. Alright. I really love the balance because if you look closely, right, plug in 0. I mean, we have these u's, so this is going to be 0. But plug in 0, sine of 0 is also 0. So this 0 makes everything 0, so we don't really have to focus too much on that. So that's cool. That's very cool. So 0, that makes everything 0. Awesome. Okay. Let me just kind of get more space here. Just try and get more space. Oh, there we go. So that's pi over 2. Okay, so let's plug in pi over 2. Pi over 2, sine pi over 2 is 1. So u square, so it's pi over 2 square, that's pi square over 4, plus pi over 2, cosine pi over 2 is 0. So we can just ignore this. So that's all 0. Pi over 2 here, that's sine pi over 2, that's 1. So it's just minus 2. Okay, so our final answer, pi square 4 minus 2. So that would be our answer. Okay, easy evaluation. Very, very nice bounds. Most integration bees will give you a nice bounds. If it gave you like something disgusting like pi over 6 or something like that, I'm sorry. No problems should be like that in integration bee. That's just making it tediousness. We have here, what do we do with this? This looks nasty a little bit. Well, if you remember your trig identity, we can turn this into sine 2x. Okay, because sine 2x is equal to 2 sine x cosine of x. So what this means is that we can turn sine of x cosine of x into a half of sine 2x. Okay, so that's what we're going to do. So we're going to be having half of x sine 2x. Now, most of the time, I don't like to bring the constant with me when I'm integrating by parts. So it's more like this when I do it. And then I just have to not forget that constant. Okay. If for some people they're more comfortable bringing it in, so they would usually bring the constant with the derivative. So most people would do that because it's just more helpful. They don't have to like lose track. So I'll do it this way for most people. So we bring the half with it. All right, fine with me. This is sine 2x. Okay, derive this, we get 1/2. Derive it again, it's 0. Integrate this, that's negative half cosine of 2x. Integrate this again, get 1/4 sine 2x. Okay, and then our diagonal is our answer. Cool. I'll have the positive term first. So half times 1/4, that's 1/8 of sine 2x minus x over 4 cosine of 2x plus c. Just like that. You know, now I think about it, maybe it is better to bring the constant with the derivative. Huh. I might try that more often. Now I think about it. It's less panicking. Ooh, this looks intimidating. very intimidating. What do you do? What do we do? What do we do? So don't overly force U-sub, right? Let's that use if we let U equal 1 over X, you know, that's we'll have inverse tangent of U, but we'll have like well actually I mean I guess we could just try it. We could try it and just take a look, right? We could sort of take a look and try it. Okay, so we know, let's see, derive this, okay. So then here, what this would look like, well, oh, I don't know why I wrote it like this. We don't have a du. So if we solve for x, right, we get 1 over u, then dx is equal to negative 1 over u squared du. Okay. Okay. And then it would look like inverse tangent of u, negative u squared du. And then I guess you could do integration by parts, but let's not go in this route though. I'll save this type of stuff for a future video. But what I was aiming for is to, well, it's the inverse tangent. Let's go ahead. You can also derive this, right? Okay. Just don't forget that it's chain rule. So it's 1 over x squared plus 1 over 1. And then the derivative of the inside is negative square x. And the reason why I prefer it this way is because, well, I'm kind of biased because I already knew this is going to happen, so it's kind of biased of me to go this route. But what's going to happen is, let's see, the negative cancels out, beautiful, and then you end up with 1 over x squared plus 1, right? Again, be very comfortable with your algebra. Multiply top and bottom. That was a bad drawing. Oh my god. Multiply top and bottom. X squared. Right? And then this becomes 1. Distribute this. This becomes 1 plus x squared. Oh shit! That's inverse tangent. So this whole bonanza here is just positive 1 over 1 plus x squared. Okay. And then, oh, look at this. And then when we continue, inverse tangent over x plus, and then the integral of x, 1 plus x squared dx. This is just a U-substitution. Oh, okay, let u equal 1 plus x squared. I'm going to skip that for the sake of time, so let's say we solved that with U-substitution and we ended up with this. Okay, and now we'll go ahead and plug in our bounds from 1 to square root of 3. Okay. Square root of 3, let's plug in square root of 3, let's get root 3, 1 over root 3, inverse tangent 1 over root 3, that's like, let's see, 1, sine, that's, sine would have 1/2, cosine would have 2/3, root 3 over 2, and then this is pi over 6, so pi over 6 here, plus 1/2 ln, and then the square root of 3, just get squared, so that's 4. This is actually, this whole thing here is equal to ln of 2, because, I mean, logarithm law, if you remember, again, be comfortable with your algebra, this is equal to, because, right, ln of 2. But you should already know that. I hope you already know that. And then minus, then we plug in 1. We plug in 1, let's say that's just 1. Inverse tangent of 1, that's pi over 4. Plus, and then a half of ln of 2. Okay. And then just to, oops. If we want to simplify this, I'll just go like that. Cool. And if you want to simplify this, this is all equal to pi root 3, 6 minus pi over 4, and then half ln, so this is ln of 2, then minus half ln of 2, so this is plus ln of 2, and then we can just leave our answer like this. Like that. I mean, you can leave your answer like this. Technically, this is allowed. You can leave your answer like this, but I mean, this is if you have more time, then it's nice to just kind of a little bit simplify it. Okay, we definitely don't know the integral of this, right? But we know the integral of this. So what that means is we will derive ln cosine of x and integrate sine of x. Okay. So the derivative of this is cosine of x, sine of x, negative. Don't forget that we are alternating signs. And then here, this is negative cosine of x. Oh, we should look at that. So this is equal to a negative cosine x, ln cosine x, and then this is, see, this is all positive that cancels out, but we have another negative here, so it's another, so it comes back with negative. This times this, cosine cancels out, so we just end up with sine of x, and then this equals to cosine x, ln cosine x, oops, plus cosine x. I was about to put plus c, but this is, it has bounds. So from 0 to pi over 3, let me make more room. Okay. So we have this now, so we go ahead and evaluate pi over 3, right? Pi over 3, cosine pi over 3. Wait, so there's so many cosine x. So I'm just going to write cosine pi over 3. This is equal, what is this equal to? That is here. So it's a half. Okay. So then that's a bad unit circle drawing. But so it's a half. Alright, so this is negative half ln half plus 1 half minus, and then cosine of 0 is 1, so it's negative 1 ln of 1. Oh, this is 0. Okay. Plus 1. Okay. So then this is equal to see, half minus 1, that's negative half. This is all. Well, I mean, that negative reciprocates this because of exponent law or logarithm law. So we technically have half of ln of 2 minus 1 half. Oh, shoot. What do we do here? Oh, well, I mean, this looks like we could try forced U-Substitution. That works. You let u equal square root of x. Well, we don't have a du, so we solve for x. So this is u squared equal x, and then derive both sides, 2u du equal dx. Alright, so now we have e to the u, 2u du. Okay, and this is just a simple integration by parts, e to the u, 2u minus 2 plus c. And so e to the u, that's e to the root x. So x squared x minus 2 plus c. Again, this looks like a composite functions, and what we like to do in composite functions is we like to do U-Substitution most of the time. So here, we could do a forced U-Substitution with this as well. So let u equal ln of x, solve for x, e to the u equals x. Then e to the u du is equal to dx. All right, so let's force u sub this. This gives cosine of u, e to the u du. This was one of the 10 integrals to memorize by heart. So this would just be e to the u half, sine of u is cosine of u. Right, and then we just plug u back in. E to the u is x, so this whole integral is x over 2 sine of ln of x cosine ln of x. Let me put an absolute value. In integration b, it's safer to put absolute value. Okay, so this looks intimidating as well, right? What do we do here? If let's see, a forced U-Substitution, that's not gonna do anything. That's just gonna, I think it would be nice to just derive this and integrate this. So let's try it, right? ln of 1 plus x, and this is x plus 1, and this is x squared over 2. Okay, so then we have x squared over 2 ln x plus 1, and minus half x squared x plus 1 dx. Ooh. Huh. So I did not teach you this, but here's what we can do. So I didn't teach you this, but this is how do I explain this? Polynomial division. Instead of doing that, I wanted to say this for intermediate users, because it's very difficult to do this fast if you're not entirely comfortable at speed integrating yet. But I guess I can share the trick here. So this is mainly for intermediate people. What I'm going to do is I'm going to do a zero substitution, right? And what that means is the reason behind zero substitution is to cancel out this x plus 1, right? So what I'm going to do is I want to add x. The reason why I want to add x is because x squared plus x is equal to x times x plus 1, right? So it factors. And what that does is this is going to cancel out this. Okay, that's why I want that x. But in order for me to have that, minus x. Okay, zero substitution. Okay, so now, I already know what my main purpose was, is to cancel out this x, and I know this is going to factor out x. So, I'll go I'm not going to rewrite the integral. So algebraically, this is just algebra. So this is x minus x, x plus 1. Okay, now what? Well, I'm going to do the same thing again, right? Because, I mean, it's very similar to the denominator, so I'm going to add 1. But then I have to do minus 1. Okay, so then this is x minus, and then, I mean, I know the purpose of the goal here. This is 1. But don't be careful. This is minus 1. This negative, and negative here cancels out. So it's plus 1, x plus 1. So this is what we actually have. So that's what it simplifies to. Let me go ahead and erase all this. X minus 1, x minus 1 plus 1 over x plus 1 dx. Okay. Very weird, but it's so useful. You have to get used to it. You have to get used to zero substitution. It is very useful. It happens a lot in integration B. So definitely very useful here. So zero substitution, you just gotta get used to it. Just get used to it. But I wanted to save that trick for intermediate users because it's very difficult to get used to because it's very uncomfortable a little bit, especially when you're new to it. Okay, so continuing, we know this is a simple integral now, so we go ahead, continue, 1 minus half of this. This is, or what you can do is you can just go like that. You just go like that, and then, okay. This is integrate this, and then integrate that. Ln x plus 1 plus c, and then you can just leave your answer like this, and you're all done. That's it. Okay? So that was a tricky one. That was a very tricky one. Holy Moses. What do we do here? This looks like a forced U-Substitution. Let u equals square root of x. We don't have a du, so we'll solve for x. Is u square equals x. 2u du is equal to dx. Okay, so now this is 2u sine of u. Alright, we'll go ahead and integrate by parts. U negative 2, 0. Oh, there's no constants here, so I can go ahead and abbreviate this. Sine, negative cosine, negative sine. Alright, and then we go ahead, integrate this. This becomes, let's see, I'll start with the positive term, because that's just me, minus 2u cosine of u. Let's see, alright, and then don't forget, plug in back your u. So our answer is 2 sine square root of x minus 2 square root of x cosine of square root of x. That was a very loud ice cream truck. And then this is your answer. And that's it. And that's all the integration by parts integrals that I have for you guys. So a lot to get used to. Please use this DI method. And then be aware of the reverse product rule. And forced U-Substitution is also very useful as well. Okay, so I hope that's very helpful for integration by parts. Again, I went very fast, so I apologize, but I just had a lot of integrals. It's going to be so much longer. But I mean, assuming you've taken Calc 2, so I hope this is review to you guys. Yeah, next part would be trigonometric integrals. So we'll really deal with trig functions a lot. And yeah, again, stay tuned, subscribe to get notified. Thank you so much for watching. I'll see you guys in the next video.